Alright, so we've been studying the SIR model, and now we're going to walk through an example in depth with many different parts to it that uses the SIR model. So we're going to talk about the disease called respiratory syncytial virus, and the description's there from the CDC website, and then please feel free to pause the video and read the setup of the problem, but due to time I'm going to just kind of go ahead and go forward. So in the prompt we're given a lot of information, and the one way that we like to first start out a problem is to kind of identify all the data that's given to us. So in this problem we're given various we should be able to determine the populations of the different compartments at time 0, at the time of initial study. And after reading the prompt, we see that the infected compartment contains 50,000 people. The recovered population is 40,000, and then basic subtraction, doing 3.32 million minus this stuff, gives us a susceptible population of 3,230,000, and that's it. Okay. B, the recovery coefficient, remember that was 1 over k, so this is going to be 1 over, and k was the number of days it takes to recover from the disease, and it says that everybody recovers after 10 days, so B is 1/10, or just writing that as a decimal, 0.1. P, the probability of coming in contact with a disease or a member of the infected population, that was 0. And as a decimal, 0.00, and then 2 more, 4. Q, that was the chance of falling ill with the disease if you are in contact, and that's 1 out of 25. Okay, so then our transmission coefficient is the product of these two, and when you do that arithmetic, you get 6 zeros, 1 6. Okay, so that we know our transmission coefficient and we know our recovery coefficient. Okay, so then we can write out the rate equations. Okay, so S, remember S was ASI. Okay, so this is negative, I should say. So this is negative 0.123451616 SI. I was ASI minus BI. Okay, so that is also the same number as before, just positive. And then minus now 0.1 I. Okay, and then R is just 0.1. It was B times I. So it's 0.1 times I. Okay, so these are the rate equations we're going to be working with. Okay, so again, all that data is just here. And our first question is, what are the populations of the various compartments on day 1? So we're given the populations at day 0. We want to figure out the populations at day 1. So what we're going to do is we're going to utilize what we call a recursive formula, where we take some old amount plus a change and to get the new amount. So the old populations, i.e. the populations on day 0, are already known. Okay, so now we just need to determine this change, and remember delta refers to a change in whatever follows, so the change in the susceptible population. From Module 1A, remember that we're going to use a straight line approximation, and we're going to say that delta S is equal to S prime delta T, and this came from the average rate of change from Module 1A. Okay, so our job is to determine what S prime is, and here we're going to use kind of a relatively big step, and we're going to actually use delta T, so the change in time, to be 1. So we're going to in 1 days, so the time units here are in days. So delta T we're going to take to be 1. Okay, so we have our rate equations. Let's just go through and do the arithmetic. So I'm only going to write this once, and then we'll just follow it through. So S prime here is minus 0.0123451616 times S, which is 32300, one more, and then times, I need to move this out of the way. Okay, times, and then let's see, that's S times I is 50,000. And if you do the calculation, you get minus, and I still need to move that. You get minus 25840. Okay, so it's the rate of change in the susceptible population, it is decreasing, negative, at 25,840 people on day 1, or day 0. Okay, the infected compartment, okay, that's all this arithmetic, and I'm going to skip that because I can actually use R prime first. So I can do R prime 0.1 times the infected population, which is 50,000. That's just 5,000 if you do the computation. And so I, it's going to be the positive this minus that. Doing the arithmetic, you're just going to get 20,840. Okay, so in total, we now know our instantaneous rate of change, and now I can determine S by doing the old, so 3230123 plus, and now it'll be S. Okay, so minus 25840. And then delta t, okay, delta t is just 1, okay? And when you do this calculation, you get 3,204,160. Okay, and feel free to do the calculations for I and R, but or write those out. But you get 70,840 for the infected compartment and 45,000. Okay. So, so that's doing all the calculations by hand, and the next part, the next part actually says to determine the population over 2 months. Okay, so certainly we don't want to do this all by hand, and we're going to actually use Excel to do this. So I'm going to minimize this window, or at least adjust it a little bit. Okay, so here in Excel, you'll notice that this is from the worksheet. So we'll be using that partially to kind of help us set up here. But I already have our transmission coefficient, recovery coefficient, and our rate equations put in here, as well as the initial populations. Now, the nice thing about Excel is if you insert a formula, and you can just drag it and copy it down to the rest of the cells. So what I'm going to do here is I'm going to enter my S prime equation. Okay, and I also want to keep in mind this little idea over here. So if I remember to drag, when I drag a formula, it auto updates. So I need to insert F4 if I do not want it to auto update the formula. Okay, so S. Okay, this is going to equal. So it's ASI. So I'm going to select my transmission coefficient, that, and now that I do not want to change each time. So I'm going to hit F4, which inserts money signs into my equation, and that means that it's fixed. When I drag it, it will not change. And so then after this, it's minus A. I need to insert, let's see. Okay, so it's minus A F4 times, now I need to select my S population multiplied by my I population. Okay, and so that's the formula I need to enter. And the nice thing about the formatting here, I have it as a table, so it'll automatically puts in any formula if I select another cell. I is going to be very similar, so it's A, again, money signs, times S times I, and then minus B. Again, I don't want B to change, so I'm going to hit F4 to insert money signs. and then times my infected population, which is just I. Okay, great. And then this is equal to 0. Actually, I can just do this, F4 times my infected population. Okay, and those are all the same numbers I got. Now to do this, to get this value, remember all I have to do is my old population plus my current population times the step value, which is just 1. Okay, and same thing here. So select that, and then plus the change in I times 1, and then lastly equals the old recovered plus the new and the step value in that one. Okay, so it's all 1, and so those were the same numbers I found before. Now to copy that down, I'm just going to highlight these 3 cells, and down in the lower right is a little black box, which if I hover over, my cursor turns to a plus sign, black cross, and I can just go ahead and drag that down and all the way to 2 months, which I'm going to call 60 days. Okay, and there we go. Okay, so on day 60, there's 10,000 people left in the susceptible compartment. Okay, and it automatically updated the S prime, I prime, and R prime. Normally, if it doesn't, you can just drag that down too. Okay, so now if I want to look at the behavior of the S compartment over time, I can just highlight these. I can highlight the I or the T and the S column. Go to Insert, and since my window is small, I'm going to go to Charts. Go to Scatter, and I can do Scatter with a smooth line and marker, and that shows the behavior of the S compartment over time. And I can do the same thing for the other ones too. But that, remember, back at the very beginning of this sequence of videos, that does look like what we want our S population or our susceptible population to do over time. Okay. So that's a brief rundown on Excel, and we're going to keep using it, but we're going to come back to it intermittently. So the next thing we're going to do is determine the threshold of the infection. And threshold here, you can see the definition and how to derive it. So it's a simple computation. The threshold here is just S is equal to B over A. Okay, B was 0.1, A was 0.1, 2, 3, 4, 5, 6, 1, 6. Okay, and doing that computation, you get 625,000. Okay, so in terms of time, we're going to make I'm going to make what I'm calling a sign chart for I prime, and so if I make a little tick mark on a number line, okay, and remember that I and I prime are both functions of time. So what I'm going to make, I don't know this exact time. Some activities that we'll do in both the worksheet and on the workbook have you analyze this stuff. But I'm just going to make a time when S prime is 0. And what happens, the threshold, this is the threshold value. What happens is I prime is initially positive, so it's increasing, right? And then after this time, whenever that is, then it starts to decrease, okay? Meaning that then the function, okay, this function starts increasing up this way, hits this point, levels out, it's 0 here, okay, so it's 0, I prime is 0, so that's a flat line, and then after this point, it starts decreasing, okay? Just like we talked about at the very beginning. Last thing is talk about quarantine. I don't have enough time in this video, so stay tuned for another video that walks through the quarantine situation.